Okay, so in today's lecture, I am going to talk all about finding extremals. Okay. So, now before I dive into finding extremals of functionals or talk about real problems of finding extremals in using calculus of variations, let us do a brief revision. So, I am going to start my topic today by describing extremals in finite dimensional calculus. Okay. So, students who have done primary courses in multivariate calculus, vector calculus, ordinary calculus, they must be familiar with most of the results that I am going to talk over the next 25 to 30 minutes. So, let me start with real valued functions of one variable, real valued functions of one variable, and how to find extremals for such functions. Now, let me just define what do we mean by the extremal. Now, extremals in real valued functions of one variable could either be maxima or minima. So, let us say we talk about minima. So, let us say I have a point x and x is inside an interval which is part of the real axis, and let us also define a function f of x such that f of x is a function from this interval a comma b to the set of all reals, and if I have if my x is the minima or respectively if x is the maxima, the definition goes simultaneously. I must have that f of x must be less than equal to f of x hat for all x hat in A B. So, that is the definition for x being the minima, and similarly if x is the maxima, this inequality is going to change around, right. So, we will have the greater than equal to inequality. Okay. So, if I have so in this case my x is known as the local sorry. So, in this case the x is known as the global minima, respectively the global maxima. X is known as the global minima, respectively the global maxima of f of x on A B. Okay. So, suppose so we can always describe that this we can collect all such points where f attains the minimal value, respectively the maximal value, and denoted by the minimal set. So, what I just said is the set of points x such that my function f of x is minimum, right. When I say minimum, I have described what do I mean by minimum, right. So, the set of points x for which f of x is minimum or respectively maximum is known as the minimal set. Okay. So, what I have is so far I have described what do I mean by the global minima or global maxima. So, in terms of the definition, if I have to write a proper math definition of a minima, that is the definition of the global minima. Similarly, if I have to write a proper definition of the local minima, then we need to look at points which are interior to the interval. So, if I have an interior point, if I have an interior point x such that x is in a b, then there exists a delta such that there is a delta positive with the condition that the value of the function at evaluated at x is the minimum among all the values of the function evaluated at all other points x hat inside a small interval around x right, then I call that my point x is the local minima, right. So, we see that the definition of the global minima follows the comparison of the function with all such values possible over the entire interval, while the definition of the local minima follows the comparison of the values of the function inside a small interval around the point under consideration. And similarly, we can describe the same definition using local maxima, right. Okay. So, if I were to draw a figure explaining all these concepts quickly, let us say I am describing a function over an interval a b as shown above, and let us say this is my function f of x, a function of one variable. We see that these are my points which are, so these are my points which are local maxima, and this is a point which is local minima, while we see that well this point is above this, well, but this point has the lowest value. So, this will be a point on the boundary which is also the global minima, because the value of the function attained at this point is the lowest among all such possible points, while finally this particular point is local maxima, right. So, in short, finding local extremals, we can always look around the points, we can always look around the neighborhood of those points, while for finding the global extrema we have to compare the value of the functional at all the points inside the interval over which the function is defined. Okay. So, then let us now start describing the tests for finding the extremals. So, in particular, let us describe the necessary condition for local extrema, right. So, we are only going to describe the necessary condition for local extrema, and then when we compare the boundary values with these local extrema, we get the global extrema when we include the boundary values. Okay. So, the necessary condition for students who have done classes in multivariate calculus, they all know that the necessary condition has to be the derivative of f of x with respect to x has to be equal to 0, right, and that can also be shown using a very simple result in the form which I state in the form of a theorem. So, the theorem says let f be a real valued function differentiable on the open interval, real valued function differentiable on the open interval I and if I have that f has a local extremum at x equal to I, then I must have that f prime of x is 0. And again the proof of this result also follows in a very straightforward manner, because let us to show the result, to prove the result, let us assume without loss of generality. So, without loss of generality, assume that x is the local max, right. We can prove similarly for local min, right. So, in this case it means that f of x must be greater than equal to f of x hat for all x hat inside the interval around x, inside a small interval around x, right, epsilon being positive. So, which means that my inequality f of x hat minus f of x must be less than equal to 0, or so which means that so let us now consider another related limit. So, we consider the following limit x hat tending to x of the ratio f of x hat minus f of x divided by x hat minus x. We know that in this ratio the numerator is always negative. However, depending on the denominator, this ratio could be positive or negative. In particular, if I have that x hat is greater than x, that is it lies on the right of x, then this ratio will be non positive. Otherwise, if x hat lies on the left of x, this will be non negative, right. Now, we know that f is a real value differentiable function. Since f is differentiable, we must have that this limit exists, right. So, let me call this as 1. So, since f is differentiable, I must have that limit in 1 described in 1 should exist, or in summary both the values, the limit whether going from the left or coming from the right or coming from the left must be equal to each other, and that can only happen if this limit is equal to 0, right, because that is the only common value from the left or from the right. And we all know that this particular limit is the derivative of the function f with respect to x, and hence the result follows. So, what is the moral of the story here? So, the moral of the story is that for a smooth function, in the interval, x minus epsilon to x plus epsilon, I have that f of x hat. I can, well, what I am trying to do is that for any smooth function f of x, I am trying to rewrite the function around the neighborhood of the point x using Taylor series expansion. Okay. So, I am using the result by Taylor's expansion. So, I know that if x hat is in the neighborhood of x, I can always represent f of x hat in terms of f of x as follows, right. So, that is the first term, and let me write one more term and then the rest will follow similarly. Okay. So, where what we have done is my quantity epsilon eta is x minus has to be x hat minus x. So, suppose suppose what I have is that x is the local max. So, suppose x is my local max, then I know that there are two pieces of information. I know that f prime x must be 0 because x is an extremum, and also f of x hat minus f of x must be less than equal to 0 because x is the local max, right. And that from these two information it follows that for sufficiently small epsilon, the leading order term in this Taylor's expansion is the second order term, and from here we conclude that f double prime of x must be less than or equal to 0, right. In fact, for local max we keep it strictly less than 0, right. Now, similarly we can show this a similar result for x being the local min. We can conclude that in this case f double prime x must be greater than 0. Okay. So, from here we get the so called sufficient condition for the existence of the extremals. So, the previous slides I showed the necessary condition, and in this slide I am highlighting the sufficient condition, and of course, I could always have that the second derivative of f with respect to x could be 0, and then we have to start again, we have to start our analysis like the one done above, starting from the third order terms onward, from order epsilon cube terms onwards. Okay. So, let us now quickly recapitulate our revision using some examples that I have compiled. So, the first example is, let us look at a function f of x. So, f of x is x square sine 1 by x, where x is non-zero, and let us say this is 0 when x is equal to 0, right. So, I know that f is differentiable. This particular example shows, it is easy to show that f is differentiable for all x except perhaps at x equal to 0, right. So, we can show that f is differentiable for all x real valued, and in fact we can further show that f is also differentiable at 0 using our definition via the limit, and the derivative at 0 is 0. So, it turns out that 0 is a stationary point, 0 is a stationary point, right. Okay. So, then what I have is, let us say that f double prime of x, when we try to calculate the second derivative of the function at 0, we see that it does not exist. All the students who are going through this exercise should do this assignment to see that the second derivative of the function at 0 does not exist, which means that, well, it does not exist. People can check that, that is because while calculating the second derivative we have to evaluate this limit sine of 1 by x at x going to 0, and we all know that this does not exist. Okay. So, that creates the problem. Okay. Well, that does not prevent us to figure out what is the nature of the stationary point, right. We know that 0 is a stationary point, but the second derivative test will not work because we can see that the second derivative does not exist. However, we see that f is a square of a real valued function, x square times sine square 1 by x. So, whatever be the value of x, we know that f of x will be non-negative, which means that the lowest value of f will be 0 and that is attained at x equal to 0, right. So, 0 is my minima. So, what I said is the following, we note that f of x is greater than equal to 0 for all x in R, and this means that x equal to 0 is a local minima, because only at 0 the function attains the lowest possible value, which is 0, right, and in fact it is also the global minimum, because that is the minimum value that the function can take. Okay. So, here is, let us quickly look at another example. So, let us consider f of x to be absolute value of x, right. So, we see that we know that this function is differentiable for all x except at x equal to 0, right. So, it is differentiable for all x which are all real values of x except at 0, and further we can see that the derivative of f of x is either minus 1 if x is negative or it is plus 1 when x is positive, which means that there is no extrema, no, well I would say no local extrema, because the first derivative is never 0, right. However, we know that f at 0 is 0, right, and we also know that f is always a non negative real valued function. So, which means that from these two observations we can conclude that 0 is a local as well as a global minima. Okay. So, this is just some basic problems which we are revising at the moment. Let us quickly again look at another example. Well, a simple case could be, let us say f of x is e to the power x. Now, this exponential function has derivatives for all orders, however, it never vanishes, none of the derivative vanishes, which means that there will not be any local extrema, right. So, f nth derivative is never 0, well all I need is the first derivative. So, f the first derivative of the function with respect to x is not 0, and from here we can conclude that there is no local extrema, right. So, our derivative test will not work on this function. Okay. So, to summarize what we have so far seen in our revision topics, what we have seen are the following basic points. In order to find a global or local extrema, what we see that if I have an interior point, x if I have an interior point x which is a global extremum, then this interior point will also be a local extremum. Okay. Now, then if I have an interior point which is, let us say well, if I have an interior point x which is also global or even local extrema, then for an interior point it is always necessary that the first derivative will vanish. So, whether it is local or whether it is global, for an interior extrema the first derivative of the function will always vanish. Finally, for points in in closed domain, for points in closed domain with boundary points included, right. We see that if the values of f at the boundary points must be checked with the values at the interior points to evaluate the extrema. So, what I just said is the following: for points in a closed domain with boundary points included, the values of f of x for boundary points must be checked with the values of the interior extremum to figure out the global values, to figure out the global extremum, right. So, this is the basic gist of our finite dimensional calculus, and we can similarly extend this one variable calculus to several variable calculus as follows. So, let me term our first case to be case A, and we can go to look at the second case as case B, that is the case with functions of several variables, x bar is x1, x2, xn being in Rn. Okay. So, like in the function similar to the observations in functions of one variable, to figure out the extremum for functions of several variables, we must have that the first derivative of these functions must vanish at each at the first derivative taken with respect to each component. So, what I just said is to find the critical points or the stationary points, let us say x bar, which is now a vector in this case, are found by setting up the following constraints. The first derivative of the function at with respect to each of the individual component variables must vanish, right. So, this result is consistent with functions of one variable, or in short we say that the gradient of the function is 0, right, and this result again follows from this one, and the one that I am going to just describe follows from our Taylor series expansion. Okay. So, then the next result is how about the sufficient condition, right. So, the sufficient condition, what we saw was for functions of one variable, the sufficient conditions led to finding the second derivative of the function and checking the sign. If the sign is negative, then local max, sign is positive, then local min. So, similarly, the sufficient condition for local min or local max, simultaneously it must be that the Hessian matrix which are the matrices involved using, let us say, the first derivatives, sorry, the second derivatives with respect to the variables, right, and so on. Let me denote this matrix in the shorthand notation del 2f del xi del xj. So, this is my matrix which is in the shorthand notation, a matrix of order n cross n of size n, and if this Hessian matrix is positive definite, this Hessian matrix is positive definite, then I have found the condition for local minimum. Simultaneously for local maximum it must be negative definite, right. So, what do I mean by positive definite? So, a matrix is positive definite if all eigenvalues are of the matrix are positive, all eigenvalues are positive, and similarly if I have a negative definite matrix, it implies that all eigenvalues must be negative. Okay. So, all we need to check to figure out the sufficient condition is to check the eigenvalues of the associated matrices that are found by evaluating this Hessian at the critical points. Okay. Okay. So, I think at this point the revision for the finite dimensional calculus is over.